In the first videos of this lecture, we have constructed a new theory, which we call General Relativity. And you may have the feeling that we basically we took this action from a hat. And well, why should that action and those equations of motion describe gravity at all? Well, the thing that you have to do now is, first of all, try to see if you recover the things that you know about gravity. That means the Newtonian theory of gravity. That's a theory that works pretty well in the solar system, and we should be able to recover it in some limit, in some non-relativistic limit. The other thing that you have to do is to try to see if there are new predictions that can be confirmed experimentally. Now we are going to deal with the first of these two things that you can do to check or to see if your theory makes sense at all, which is this Newtonian limit. And we are going to deal with this Newtonian limit in two steps. First, we are going to take a sort of a special relativistic limit. It is the weak field limit. The Newtonian theory is linear, while, as we stressed when we derived the equations, the Einstein equations are nonlinear and contain self-interactions of the gravitational field. Then we expect that in order to recover the Newtonian limit, first we have to linearize the theory. We have to linearize general relativity, and in this generalization we are going to get a special relativistic theory of gravity. And okay, you have heard me say several times that there is no special relativistic theory of gravity, but I have to say that there is no consistent special relativistic theory of gravity. Not fully consistent, but there is, in some approximation, there is a theory that works well, and I mean, you can increase the precision of this approximation, adding more orders. This approximation, this special relativistic approximation, which is the weak field approximation, is extremely useful. You have to take into account that practically all the phenomena that happen in the solar system, all the gravitational phenomena, are weak field phenomena from the point of view of gravity, and you should be able to recover everything, okay, all the experimental results from this weak field limit. On the other hand, this weak field limit, being a sort of incomplete special relativistic theory of gravity, will help us to understand many things and to deal with approximate quantities like a sort of energy momentum tensor for the gravitational field and so on. So this is a very important subject. When we study gravitational waves, we will also make use of this weak field limit, because it is in this weak field limit that we obtain the wave equation for the perturbations of the gravitational field. So what is the setup? Okay, weak field means weak gravity. When there is no gravity, we have the Minkowski metric. So you could say that the weak gravitational field can be expanded around this Minkowski spacetime. And the perturbation we call h mu nu, or if you want, maybe delta g mu nu, and we consider it to be small. And to control the smallness of this perturbation, we define it in this way. So there is a parameter chi that will be small, and field h mu nu. This chi is defined such that chi squared is 16 pi g over cq. In natural units, remember that this will be like LP squared, so basically this is like the Planck length, this chi, up to this normalization and so on. This is the setup, and now the idea is to find the equations satisfied by this h mu nu, because eta mu nu is just fixed. the new variable, which is small or whatever, is h mu. We want to find the equation motion for this h mu, and we are going to expand the Einstein equations just to first order in h, ignoring terms of order h squared or equivalently of order chi squared. Okay, I need one definition first. Okay, I am going to deal with this h mu as if it was a special relativistic field. So when I write h mu, I'm going to mean eta mu rho, eta nu sigma, h rho sigma. Okay, this is to this order, this is the same as g mu rho, d nu sigma, h rho sigma plus terms of order h squared and higher. So this is why we are going to use this. It is approximately true that you could raise the indices with g, and this would be equivalent to raising them with eta up to this order. But let's take this definition as exact, because as we are going to see, it just works this way. Okay, that we can deal with h as a special relativistic field. The first thing that you have to do is to compute the Christoffel symbols. We want to expand the Einstein equations, so we need to expand the curvature in this weak field limit, and the curvature contains the connection, so the connection contains the derivatives of g and g inverse, so we need g inverse and then the derivatives of g. Okay, so g inverse is not difficult to see. That can be computed, that it is equal to this. Okay, to this order, always plus terms of order h squared, and this is something that can be proven. Okay, if you multiply this by, for instance, g nu rho, this is eta mu nu minus chi h mu nu, and this is eta nu rho plus chi h nu rho, and this is delta mu rho minus chi and h mu and rho with index down. Then I multiply this by this, and I get plus chi, and this raises this index nu. It is h mu rho plus terms of order h squared. But you see that these two cancel, so one is the inverse of the other to this order. Now let us compute the connection. Okay, I could write this. Sorry, I need different indices, so rho sigma minus chi h rho sigma to this order, and then remember that we have partial mu, and this would be g. I'll write it and then I will substitute g by the approximate expression. Okay. G nu sigma plus partial nu g mu sigma minus partial sigma g mu nu. Okay, now I am going to replace g by eta plus delta g, or eta plus chi h. Eta is constant, so the only thing that contributes here is the second term, chi h. This means that I have a global factor of chi. Okay, and that all this will be replaced by h to this order. But then, since there is already a chi here, or and there is a chi here, this term does not contribute at all, and what we have is just 1/2 of chi eta rho sigma partial mu h nu sigma plus partial mu h mu sigma minus partial sigma h mu nu. As usual, plus terms of order h squared. Not so difficult. But Okay, this is omega has no ordered zero term. We could have seen this in this way. Gamma would be gamma of eta plus you want delta gamma. Okay, the first order variation, but you know that the gamma for eta, and we are working in Cartesian coordinates, is 0, so you only have delta gamma, which is of first order in chi. The consequence of this is that gamma, all the terms gamma gamma is r of order h squared or chi squared, and we can ignore them. Then we only need to consider the terms with partial derivatives of gamma in the computation of the Riemann tensor. These terms are 2 times partial mu gamma nu rho sigma, okay, plus then we know that the rest are terms of second order in h squared. This clearly simplifies the situation a lot, and let's do this. This factor of 2 and this 1/2 cancel. There is chi, and there is eta. Okay, here the index is sigma, so I need sigma and maybe another index lambda. Partial mu I will antisymmetrize later, so first let me write this expression. This will be the indices are nu and rho, so it's h nu rho and then lambda plus the symmetric rho nu lambda minus partial lambda h nu rho. Okay, and then I antisymmetrize in mu and nu. But if I antisymmetrize in mu and nu, when I have to do it in more terms, I have to do it like this. Okay, and it is understood that this side of the antisymmetrizer matches this side of the antisymmetrizer. But here I have two partial derivatives antisymmetrized, so this term vanishes. I only have these two, chi eta sigma lambda, and then two terms, partial mu, let's do it right rho first, just because it is simpler, minus partial lambda, partial mu h nu rho. Okay, these are the two terms. Now if you want to simplify it a bit further, you can raise the index lambda and change it by sigma. Okay, and then eliminate this, and this is to second order the Riemann tensor. Well, the Ricci tensor that appears in the equations, in the Einstein equations, is obtained by identifying nu and sigma, and here it is good when you have this kind of contractions. Here you are contracting sigma and nu, but nu is antisymmetrized. So in order not to make any mistakes, it is good to expand this antisymmetrizer. So let's first I expand, and then we just partial mu h nu sigma rho mu h mu sigma minus partial sigma mu h nu rho plus partial sigma partial nu h mu rho. As usual, plus terms of order h squared, and now I identify nu and sigma. So here sigma and sigma. Okay, we define h as the trace of h mu nu with eta. Okay. And that partial square is just partial mu, or the other way around. So this is h, and this is partial square, and then r mu rho, this is the result, will be chi over 2 partial mu partial rho h minus partial rho partial sigma h mu sigma minus partial sigma partial mu h sigma. Let's do this. Let's interchange partial mu, and let's raise this index and lower this one, so we have a term like this. Okay, and then you realize that this is nothing but this. You can combine these two terms. They are symmetric in rho and mu, as you expect, because the Ricci tensor is symmetric in rho and mu. And then the last term is just partial square h mu rho, which is also symmetric in mu and rho, and this would be the Ricci tensor. Okay, this is a first order in chi. So what happens for r? Well, it is r mu rho contracted with the inverse metric. Since this is of order chi, only eta mu rho does something here, so it will be, because if I consider the other term, will be of second order, so this gives partial square h minus 2, okay, let's write this as partial nu h mu nu plus partial square h. Okay, so you get a factor of 2 here. We remove this term, and now we cancel this factor of 2 here and here. Okay, plus terms of order h squared. Okay, well, the last thing that we need to do is to combine both r mu nu and r into the Einstein tensor. And since r is of order chi, instead of g, we will have to disorder eta mu nu, and everything will be of order chi, of course. There is a half here and a half here, so I take chi over 2 as a common factor, and I write partial mu h minus 2 partial mu partial, if you want, sigma h nu sigma. This is equivalent to what I wrote before, of course, plus partial square h mu rho, and then minus eta mu nu partial square h minus partial alpha partial beta h alpha beta. Okay, plus terms of order h squared. Okay. Instead of dealing with this complicated thing, let's give it a name. So let's say that g mu nu is just chi over 2 and something that I will write as d mu nu of h. Okay, so d mu nu of h equal to 0 is what is called are called the first Pauli equations. And okay, they arise as the Wakefield limit of the general equations of general relativity, But Fritz and Pauli obtained them in a completely different way. They consider the problem of a spin 2 field in Minkowski space-time. A spin 2 field is a symmetric rank 2 tensor in Minkowski space-time, and they try to construct a theory that has certain properties. One of the properties that it has to have is that it is invariant under certain transformations, which we will study at some point. Why we need those transformations? Well, the same way we need gauge transformations for a mu, because we want to remove unwanted degrees of freedom. A mu has too many components, and it is meant to describe only two, the two polarization states of the photon. H mu nu has a lot more components, and it's also meant to describe only the two polarization states of the spin 2 particle, of a massless spin 2 particle. So you need more symmetry. This is the action that has this symmetry. Okay, and they obtained it, and of course, from this point of view, this is a free spin 2 field. Indeed, there are no self-interactions of any kind, and there are no sources either. So these are the equations of the free spin 2 field, or the Fierz-Pauli equations. The idea of the graviton arises precisely from these equations in this limit. The excitations of the spin 2 field will be spin 2 particles, and these spin 2 particles are the gravitons. Okay, now let's go on. And let's consider the coupling to matter of, okay, so this is in these units that we are using, and with this chi, the Einstein equations in presence of matter have this form, but in this side we have 1/2 chi d mu nu of h, and the other side we have chi squared over 2c. And let me write this as t mu nu, because this is of order chi squared. Okay, so the right thing to do would be really to add things of the same order here, and we have ignored them. Okay, this is the first problem that you meet. This is not so consistent. We have ignored these self-interaction terms, but you should add them here. Okay. On the other hand, what is this T mu nu? Well, this is the T mu nu of matter, but you have to. It usually contains the metric field, and you also have to expand the metric field there in perturbations around Minkowski. This is the lowest order, and this is the one that you obtain setting G equal to eta. And this is the Rosenfeld energy momentum tensor in Minkowski spacetime. Okay, so you see that there is something already not quite right in this approximation that finally takes this form. It is just chi over c t mu nu Rosenfeld. So this would be the equations in terms of these variables. It is not quite right because, as I said, we have ignored to obtain this part. We have ignored all terms of second order in H, and here we are already adding a term of second order in H. From the purely special relativistic point of view, let's see if how consistent is this. Okay, you can prove that this side satisfies this equation of shell. Now you have seen many of these relations, and it is due to the fact that it has this gauge symmetry that Fierz and Pauli constructed. They built in this theory, and for us, as we will see, is just symmetry inherited from general coordinate invariance, nothing else. So you expect the conservation of this as well, by consistency. However, how can this energy momentum tensor be conserved if it is in interaction with the gravitational field. This just cannot happen. It's not really consistent. Certainly not from the physical point of view. You would expect really that the consistent thing would be to add the gravitational energy momentum tensor, and that both of them are conserved. It's just the total energy momentum tensor that it is conserved because there are interactions between them. However, if you add this term here, this term would be of the same order as this one, chi, so they would add up. The conclusion that we have reached through all this discussion is that the consistency demands that we include the energy momentum tensor of the gravitational field H to second order. This will be something of second order, so because there might be higher order contributions. So let us now examine what happens in absence of matter. We would have this kind of equation, and let's see if this is now consistent. Okay, we have that this is 0. Okay, and how about the conservation of this T mu? We know that it is conservation on shell, so this means that this is going to be proportional to these equations, okay, times something else. But now the question is not that this is 0. This was 0 before we introduced this T mu. Now the equations are d mu equal to T mu. So this energy momentum tensor, which was computed with the original theory, if you want, from the theory that gives you this d mu, now would not vanish. Okay, so it would have terms of okay, something like t and derivatives of h, something of third order. Okay, this is because now you have interactions of higher order, and the only way to fix this is to add a term of higher order to the energy momentum tensor. But now this problem, you fix this problem to certain order, and this problem is going to arise again to the next order. The conclusion is that you have to add an infinite series of terms. And adding an infinite series of terms, what you get is the vacuum Einstein equation. Okay, and this can be proven. Okay, so this is interesting because it confirms what I told you, that there is no special relativistic theory of gravity, that it has inconsistencies. Okay, these inconsistencies are discovered when you try to couple it to matter, because then you see that the conservation of the energy does not make much sense without taking into account the interaction. And the moment you take into account the interaction, the equation that you get just for the gravitational field is not consistent as it is, and in order to make it consistent, you are forced to introduce further terms, and you go back to general relativity. So the special relativistic theory of gravity, which is consistent, is essentially equivalent to general relativity written in some different variables, which are these h mu's. This is something very nice, and it is a result that has been discussed in the literature. I can give you references if you want about it, but this is all we are going to say about it. Okay, let me go back to the gauge invariance that Fritz and Pauli used to construct these actions. So basically, they consider all the possible terms with these equations of motion. They consider all the possible terms that contain two derivatives of h, and they checked which combination gives you is invariant under these transformations. Okay, you will see that they are, well, more or less what you expect. Okay, they are generalization of the gauge transformations of the electromagnetic field, but more interestingly, this is exactly what you get from the transformations of under general coordinate transformations of the metric. These transformations are of this form. Okay, this is a transformation of the full thing, so of h mu nu. Okay, so this is a transformation of h eta mu nu plus chi h mu nu. So if you look for the term of first order in chi here, okay, you will find that it is exactly this one. Although to be consistent, really you need to introduce chi here. Okay, this is just normalizing this parameter, because here the units of h mu nu are not the same as the metric. The metric was a-dimensional. H mu nu has dimensions of length -1. Okay, this means that this parameter needs to be a-dimensional, and in order to fit the dimensions of everything, you need to introduce this chi here when you write the transformation of the metric. So by doing this, you get automatically this. Then the moment you have gauge symmetry in your action, you will have a Bianchi identity, or an ether identity, sorry, like this. But there is another way of seeing this related to the invariance under general coordinate transformations of general relativity. You know, you have this contracted Bianchi identity, and if you expand this identity, it will become just this. So okay, this is due to general covariance. This is general covariance. In the limit in which it becomes this simple transformation, you get this, which is also what you get in the same limit. So all these things fit. If you have gauge symmetry, you can use this gauge symmetry to simplify the form of the equations, and there are, by fixing the gauge, there are a couple of gauges which are very useful and commonly used. One of them is called the transverse traceless gauge. Transverse means that it satisfies this condition. Traceless means that the trace is 0. Okay, this greatly simplifies the equations. And another popular gauge is the Donder gauge. The Donder gauge is expressed in terms of a variable which is called h bar mu nu. H bar mu nu is defined as h mu nu minus a half eta mu nu h. And in terms of this variable, you can check that if you impose this gauge, this is the Donder gauge, then the equations of motion, these fifth Pauli equations, take a very simplified form, which is partial square h bar mu nu, and in vacuum this is just 0, and this is the wave operator. So you see that this approximation, this variable h bar, okay, will have solutions that have the form of waves, and these are the gravitational waves that have been observed not so long ago. Okay, in more general cases, instead of 0, what you will have is something like this. And in this approximation, you can use, well, if you know the T mu nu produced by some masses moving, okay, then you can compute what are the waves produced by them. This can be considered a source for the waves.